Alright, compositions of functions. There's only one definition term this week, so I wrote it in for you, and rather than giving you the teacher notes. Alright, compositions of functions involve two separate functions, and we'll begin by singly identifying values within the function, and then we'll move in slowly to how compositions of functions relate to one another. So f of 4, pretty simple. Identify your function by the variable used and insert by substitution the x value, and the answer is 16. Again, for the second one, it'll be -2 substituted in for x, and remember, any negative number squared becomes positive. Alright, g, now we'll be switching to the other, and we'll be substituting 3 for x, and you get the square root of 4, which is 2. -3, the square root of -3 plus 1 is the square root of -2. No real solution. We will work on this when we get to quadratics. Alright, this one is using operations to form composition functions. F plus g of x simply means you will add the f function to the g function, combine like terms if possible, and we are done. Same thing here. Combine like terms, not possible, so we are done. Same thing here. X squared times the square root of x plus 1. F divided by g of x squared divided by the square root of x plus 1. Alright, now we get into our compositions of functions. Or sorry, f of x. F times f of x looks like this. X squared times x squared, which can be simplified to x to the 4th power. G of f of x means that you will substitute the f of x function into the x value of the g function. So it looks like this. The square root of x squared plus 1. Now we'll look at graphical representation of compositions of functions. We'll be moving back and forth between the two functions, so pay particular attention to which graph you're supposed to be on based on which value you're looking at for your variables. So f of 0, that is 8. F of 3, that is -1. G of 4 is not possible. It is not part of the solution set. It is not on the line. Does not exist. F of g of 0. Now we get into compositions. When you're dealing with compositions of functions, remember you're going to work from the inside to the outside to find your values. Okay? Remember that the input of the inside becomes the output of the inside value becomes the input of the outside function, and then you get your answer. Alright? G of 0 is the number 2. If g of 0 equals 2, I will substitute 2 in for g of 0 and get f of 2. And move back to the other function, or the other graph, and f of 2 equals 0. G of -1. There's supposed to be a second set of parentheses there. G of -1. Always work from the inside out. G of -1 is 1.5. The output of the inside function becomes the input of the outside function. So I will substitute f of 1.5, and 1.5 is 1. Now we'll look at it in reverse. F of 2. F of 2 is here. That is the number 0. 0 gets substituted for f of 2, so g of 0 is 2. Alright, when does f of g of x equal 8? Now what we'll be doing is working backwards. One way to do this is by finding your first x value, your first y value, your second x value, and your second y value. Once you work backwards this way, you will see how you can make it through to the original answer. So we know that the end result, the second y value, the second output that we are looking for is 8. So we need the corresponding x value for that second output. Remember, we're working from the outside in. So we will be looking at the f function when y equals 8. Y equals 8, so at that place x equals 0. Now remember, in compositions of function, this becomes that. This first output becomes the second input. So since we're working backwards, this input becomes that output. Now we go to g. When y equals 0, x equals, when y equals 0, x equals 2. X also equals negative 1.5. Is it possible for g of x to equal negative 3? Alright, well, let's test that out. Remember, we're looking for the first value from the last value. So let's start with the output of negative 3. Negative 3 in the g function, negative 3 in the g function, well, that's down here. Notice that is nowhere on the line, so the answer to that question is no. Moving here, two functions are inverses of each other. If they're one-to-one, they are f of g of x equals x. It will simplify to that if they are one-to-one. So we will test that using this. So it's going to be 4 times, substitute the x value, or the g function into the x value of the f function. 1/4 x plus 1 minus 4. Notice I have just followed this pattern right here. F of g of x. Substitute the second into the first x. Use the distributive property to determine that x plus 4 minus 4. These two cancel out. The answer is x. That fits the one-to-one. The answer is yes. In this one, negative 1/3 x minus, negative 1/3, substitute g into that x value, times 3x minus 3 minus 1. The distributive property tells me that this will become negative x plus 3. Wow, my fault. Plus 1 minus 1. These cancel out. What's left is negative x. Negative x is not x, so the answer is no. Okay? Down here, we'll be using compositions of functions to determine domain. Please remember, if there's a domain restriction in one of the two functions that make up the composition, then you have a restriction in the overall domain of the composition function. Okay, new terminology, but it's written the exact same way as we're familiar with. F of g of x is the way that you would rewrite this in our in the function notation that you're used to. Okay, so that means I'm going to take g, insert it into f, and now I get the square root of x squared minus 1. Now please remember, the domain restriction of the g function supersedes any simplification that could follow after you combine the two functions together. Notice that these two will cancel each other out, thus leaving no domain restriction. However, because there is one in the original function, there will be one in the overall composition function, which means that the answer to this is... Now, we go over here and we do the exact same thing, except it's g of f of x. Given that information, now we'll be inserting the f function, x squared minus 1, into the g function. Now what we have here is a restriction because this number cannot be less than 0, cannot be negative. Alright, so that means that we have to find the place where this function is negative, or when it is equal to 0. Okay? So remember, a squared number always becomes positive, which means that -1 and +1 both will give you a result of 0. But that also means that any value between -1 and +1 must be negative, because it will be smaller than -1, therefore leaving you a negative value. So that means that the domain restriction here will be -infinity to -1, inclusive, and 1 to +infinity. Please work on example number 6 and be prepared to share your answers when you get back to class tomorrow.